Hello, everybody. So we are still talking about the points that we want to cover before we start talking about the systematic approach that we will follow to solve mass balance problems. So this problem that we see here is about a separator. This is going to be an introduction to the point that I want to make, that we have a separator, we have a feed stream which contains water and ethanol. We know the flow, the mole fractions, and we know the mole fractions of the top product and the bottom product from the separator, and we want to calculate the missing flow rates. And to do this, we will put the mass balance equations and try to see if we can solve them together. So for the water, we will have water in stream 1 equal water in stream 2 plus water in stream 3. The same for ethanol, and we have the total, whereas N1 is equal to N2 plus N3. So these are the three equations that we have, and we know that these are only two equations, and that the third equation is a dependent equation. So this is these are two equations and three unknowns, and if we look at these equations, we will notice that we cannot solve them. And the reason we cannot solve them is that we don't have any given flow rates. And this is a very important thing. No matter for how much information you have, and no matter if you have any more equations or any more information, if there is not at least one flow rate, we will not be able to solve this problem. So this is one thing that you have to keep in mind and check on before starting solving any problem, is that you have at least one quantity or one flow rate. Having all the information as compositions is not enough. We need to have at least one flow rate. So if I don't have a flow rate, I have to assume one, and this assumed flow rate, we call it a basis. So a basis is any value or a value of a flow rate or a quantity that we assume in order to make the problem solvable. So the question is, which value should I or which variable should I assume, and what is the value? You have the freedom to assume any value in any stream. This is something that is totally up to you. Especially for a simple problem like this, it's just one unit. You have the freedom to pick any value or any parameter. But if you have a big flow sheet with a big number of units and big number of streams, there will be some criteria on which we can tell which one will make the solution easier. But for now, and we will go through this in details later. But for now, let's agree that we have to have at least one flow rate, and this is what we are going to do now. So I'm going to assume a value of the flow rate which is 100 gram moles per second for stream 1 as a total molar flow rate. And based on this, we have the three equations. We substituted with N1 as 100, and then we can calculate the values of N2 and N3 by solving any two of these three equations. And we are done with this problem. So this is a very important thing, that we have to have at least one flow rate. Now, just to give an introduction to the next point. Let's say I assume the basis and I solve the problem. Everything is done. The mass balance is okay. Mass is conserved. Mass in equals mass out, and everything is fine. Now I want to, or I knew after I'm done with the calculations, I knew that the flow rate that I want is not 100 gram moles per second of N1. I want, let's say, 500 gram moles per second of N2. This is the goal, and this was an information that I didn't know in the beginning, and I knew this later. Or I have some updates to my data that based on this I knew that the value of N2 should be 500 gram moles per second. What I would think of is that I will repeat the calculations again. So I'll start all over from the beginning. I I write the equations, and based on the equations I substitute with N3 as 500 gram moles per second, and then I redo the simultaneous solution of the equations. This is one option. However, there is a very easy option, and it's a very time saving option, which is what we call the flow rate scaling. Flow rate scaling means that I can, if I have a problem like this, I have 500 kilograms per hour of benzene and 500 kilograms per hour of toluene, and then we have the product is 1000 kilograms per hour, 50% benzene and 50% toluene by mass, and I want to find out how much benzene and toluene should I have. Of course, this is just for a demonstration. If I want the product to be 3000 kilogram per hour, what you can do is what we call the scaling, is that we are still maintaining the mass balance, but we are changing numbers, and the numbers are changing by multiplying all the flow rates by a factor. So this factor can be 3000 if I want M3 to be 3000, and then I multiply also the flow rate of stream 1 and flow rate of stream 2 by the same factor. Still the mass balance, as I said, is conserved. I have 1500 plus 1500 equals 3000, so it's still conserved, and I didn't have to redo the calculations one more time. I'm already using the values that were there already. There is one other thing that is very nice, is that I can use this scaling to convert the units. So I can use the same flow rates, and I just change all the units from kilogram per hour to pound mass per second. This is one other option. Still the units are the mass is conserved. There is no problem with the calculations. Of course, this doesn't include the compositions. The compositions, as we said before, is independent on the quantity, so it's not gonna depend on the quantity when I scale up or scale down. Scale up and scale down, if the factor is larger than 1, I'm scaling up, I'm increasing the flow rates, and the opposite if I'm scaling down. There is one important note here, is that I can do this changing of units for the same unit, meaning that I can change the units of mass to mass, or from units of moles to another unit of moles. I cannot do this from mass to moles or from moles to mass. So this is a very, very important point. So these are two things that I wanted to cover here, and from this we can take some notes. Is that for a problem to be solved, I need to calculate some unknown variables, and in order to do this, I have to have number of equations equal number of variables. So this is a very well-known thing, and we don't need to stress on this, but this is a very well-known thing, that I have to know if the number of equations I have are enough or not before I even start to solve the problem. And this is something we will discuss later, and we will know how to do this. The second is that the maximum number of independent equations for a unit is equal to the number of species involved in this unit, which is something we covered last time, and that we have to be smart when we deal with the equations, and this is something we will see later, that we can write the equations and then we will pick the equations that are easy to solve. So this is one thing we will discuss later. And finally, that we have to have at least one flow rate. If we don't have flow rate, we have to assume a basis. There is only one point left next time, which is going to be covered in this example, and after this we will start to go with our systematic approach of degrees of freedom analysis, which we are starting next time, inshallah. So I'll see you then.